So this hasn't been emphasized, but you probably have been seeing or noticing maybe you're doing a lot of reactions that start with one reactant going to other things. And if you go back into kinetics here, and you measure everything that's radioactive, that reactant follows first order kinetics every single time. And what that means is that we're allowed to use this equation. Now, in the context of nuclear chemistry, instead of a K there, we use a lambda. I know that seems weird, right? But it's the same exact equation. So the biggest difference is that we have tables and tables and tables of like uranium-235 or thorium-238. You just look it up and it gives the half-lives. And all of those are time units, so a certain number of years for each of them. You plug it in and you solve this the exact same way that you solved it before. Two other things to note. Don't forget that you can still use the little percentage thing. That will come up. And so it might say that, at, what time is the reaction, is 25% remaining. Again, remember, remaining is good. That's the number you want to put on top. And remember, you're always going to put it over 100. If it asks you about decayed and it says at 25% decayed, that is not the same thing as the 25% remaining. In that case, it would be 75 over 100. So don't forget that. And then don't forget that there's the other little trick. And this is much more of a deal because when you're looking at radioactive stuff, most of it's solid chunks of stuff and you're not trying to really even dissolve them in any liquid. But you can take that exact same equation and remember that those brackets up here mean molarity. And so that represents moles of A at some time over moles of A initially. And so, like, if we did have a solution, the solution itself is the same solution even as time goes by. It's not changing. So the liters cancel. And then because A is the same thing, I can use the molar mass of A, and it's going to be the same molar mass for either of them because the only difference is how much time has passed. They aren't changing molar masses. So I put that on there backwards. That's supposed to be moles on bottom. There we go. Moles over grams. Moles over grams. And so our moles now cancel, and that means that we can put this equation in terms of grams over grams. So we have mass of something over the mass of something over equals negative lambda times T. And so this equation right here is very, very commonly used in radiochemistry. So this is nothing new. You've done plenty of examples with this before, but you just need to know that this is a very important reaction. It's kind of considered fundamental for radiochemistry.